Hello, welcome back. I want to look at a big concept in Rust, which is ownership. Now, I know what you're thinking. Hey, didn't we just have hello world, print line, hello world, and now we're going and skipping a few things? Aren't there a few things we should go through? Well, yeah, we will go through those, but personally, when I was learning languages, I always hated that chapter 2 was integers, data types. Made me want to throw the book in the bin. Do we really have to learn what an integer is for the 10th time? Anyway, ownership is a really important concept. To start things off, I'm going to look at the difference in memory types between what we call stack and heap. Okay, hopefully this is familiar to you. We'll go through it. So the differences between them, a stack is very small, about on the order of several megabytes. It's pretty easy to fill that up and have a stack overflow. Now, if we're doing normal programming, it's not hard. If we're doing normal programming, that'll never happen. But if we're trying, it's not that hard. I've done it before. Whereas a heap is really big. My system has 64 gigabytes. I can allocate a gigabyte here, a gigabyte there. It handles it just fine. Okay, a stack is used for local variables and function calls. It remembers which function was just recently called, which function is currently being called, and it also stores any local variables. On the other hand, heap is for generalized data. So the obvious ones for programming, game programming, would be images, model data, but then even just the objects in the game world that we're working with, they can be allocated on the heap. Now, with the stack, anything we allocate, the size is known at compile time. So before the code is run, the compiler can look at the code and say, over here, where you are making a variable, that's an integer, I know how many bytes that's going to take up. Whereas in the heap, the size is unknown, and it's we sort of request memory dynamically. So it's a data structure where we can request any amount of memory, and that sort of compiler does its best. Okay, so what else do we have? Variables on the stack are cleaned up when out of scope. And variables on the heap, memory which is allocated on the heap, is persistent. It sticks around. And we have to remember to free that by hand. So here's an example in C++ of allocating on the heap. Let's have some function. And we'll allocate a number of bytes, so an array of bytes. And then we just return. Okay, so let's have a look at the memory when this is performed. Okay, so for the stack, let me just do this up. Some memory locations. And let me go, oh, something I missed. Whoops. Put another variable in there. Okay, so currently we are in this function. It has been called with a variable of 10, value of 10 for I. And so we're going to allocate 10 characters. And once this allocation is performed, the memory location of the start of that memory block is returned to handle. This pointer handle actually stores a few other bits of metadata, but it's not really so important. And we also remember the function that we called from originally, and there's some other things back here. So when this function ends, everything is popped off. Now on the heap, we have this chunk of memory, which is what handle is referring to. That's the significance of handle. It's the beginning of the memory chunk. And we have some memory before and after. This is the memory which has been allocated. Now, when this ends, these variables are popped from the stack. So this is now meaningless. Handle is now meaningless. I is now meaningless. And we return to whatever we were doing in the calling function. There's an issue though. This allocated memory has not been freed. The computer has simply forgotten where it was. Whoops. So we have a number of problems. Here are some common issues, common bits of fun we can run into in C++. First of all, we could trigger a memory leak. And that's what this example is demonstrating. So in other words, handle has been deleted, but our program just forgot where the allocated memory was sitting. That doesn't mean that we have actually freed that memory. Okay. Then we could have a dangling pointer. So a dangling pointer issue is if we have a pointer which is pointing to a memory chunk, and then we call a function which frees that memory, but I mean, the pointer is still a number, 0x32, whatever. So we could, after that memory has been freed, attempt to access the contents of the pointer. This is a dangling pointer, right? Because it's not pointing at valid memory. If we're lucky, this gives us an error. If we're unlucky, it just does whatever, completely random, very hard to find. And then another example is double deletion. And that is, let's say we have multiple pointers which refer to the same memory location. And we go to pointer 1, we say free your memory. And then we go to pointer 2 and we say free your memory. Well, wait, that memory's already been freed. So again, if we're lucky, it gives us an error. If we're unlucky, it does something random, which is very hard to find. So how does C++ address this? Okay, the first approach is this one. Get good. I got to say, I am guilty of this. I have done this quite a lot, probably still. Being aware of these issues does force you to write code in a memory secure way. It's not ideal though. It's not fast. I mean, how much fun are segfaults? Okay, the other approach is smart pointers. So a smart pointer is a pointer which includes a lot of other bits of metadata. For instance, the number of sort of references. It sort of counts references to the thing, the memory chunk that it's pointing at. So you can have shared pointers where if the memory is freed on one pointer, it's automatically freed on all pointers. You can have unique pointers where only one pointer can point to a memory block at any time. The issue with this is that the implementation for these is kind of like doing garbage collection. And the problem is Rust is a systems level programming language, which means we do not have a garbage collector. That's just too much overhead. If only there was a smart way to, a better way to do it. The third approach, this is pretty similar to what Rust does, is RAII, Resource Acquisition is Initialization. It's a really confusing, weird way of saying that some C++ data structures, when they go out of scope, their memory, underlying memory is deleted. Things like std string, vector, array, many, many others. Most of the data structures implemented in the standard library do implement RAII. So for those, we don't have to worry so much. Now, the Rust solution is something called ownership. So very briefly, ownership. Here's the gospel. Ownership is a system where a chunk of memory is owned by one and only one variable. When it goes out of scope, that memory is freed. Ownership can be transferred or borrowed, and when a variable transfers ownership of its memory to another variable, the original variable is invalidated. So to bring it back to that original diagram, okay, let's say the variable handle is destroyed. In C++, we would probably not be able to go back and free this memory because there's no guarantee that something else isn't relying on it. But if we have ownership, then the compiler can automatically free memory when a variable is destroyed. There's no there's no reference counting or anything, so no weird garbage collection stuff. Anyway, ownership. So enough talk, let's jump over to the code. Okay, so I'm going to go through a series of code samples and sort of explain them. And yes, if you're familiar with the Rust book, these are sort of taken from there. But again, they are great examples, and I can only be so creative when we're going through these beginner topics, these fundamental topics. So let's make a string. And print it out. So it's great to think about this. For a string, when we make a string, are we necessarily allocating memory on the stack or the heap? And the answer is, in general, on the heap. And the reason is, yeah, right now, I've hard-coded a string, so the compiler does know the size of the thing that I'm allocating. But in general, this function does not necessarily know, it's not a fixed thing, the size of what I'm allocating. So this would be allocating on the heap. Print it out, we have this, and remember, when this function ends, or it's the main, so everything's always freed, but if this was a function, when it ended, line, the underlying memory would be deleted along with the variable line. Okay, so here we've made a string, so we've allocated some memory, and then we set this equal to another variable. Now this isn't going to work so well. We can print out S2, that's fine. But if we attempt to print S1, we get an error. And it says, borrow of moved value. This is not good grammar. But anyway, the point is, S1 has transferred ownership of its underlying memory to S2. And so it's no longer valid. It's been invalidated. This will throw an error, and it throws the error before we compile. So that's really good. Now, if we wanted to actually have two copies, no problem. We can just call the clone function, and this gives us an identical copy. It allocates new memory. So we could then print both of these, and this would not throw an error. Yeah, this is something, this is something. It certainly is. Okay, how about another data type? Let's go I1 for int1. Okay, let's try to do the same thing. Interesting. There's no error. Why is that? Well, it's good to think about data. Here we just have a number. We know it's an int32, and this is what we call a primitive data type, because no matter what value an int32 has, we know that it takes 32 bits or 4 bytes. So the compiler does not have to guess about how much space to allocate for that, and so I1 is on the stack and no underlying memory is allocated. This means that I2 can be a copy of I1 with no issue because they don't own anything. They're quite simple variables. Okay, now let's have a look at another example. Okay, so we start with a string and a 32-bit integer. We call this function. Now the difference between, okay, let's play with this. So we'll go, right, so after this variable has been passed into a function, that function actually takes ownership of the variable, and so line is invalidated, which is why this bit here is complaining. So get rid of that. So in new line, we now have ownership, and this is sort of a big difference between Rust and C++, because in C++, the arguments to functions are very much temporary variables. They're not that important. They're cleaned up and stuff. But anyway, we have the ownership, so we can work with this one and print it out. Now, just note, I'm putting mutable, and this is indicating that something is not constant. So in Rust, by default, variables are immutable or constant, and we have to specify if we want to change them. Now, here we have an integer. We can pass that in, and because int32s are simple data types, no underlying memory exists, and so no ownership. Ownership is not an issue, basically. And we can grab that. Now if we run this, okay, we have hello world, and the variable x can be copied. 2 times 7 is 14, and the original x is still maintained. 3 times 7 is 21. Okay. All right, so what if we want to get things back? Well, it's very simple. Functions can return ownership, but of course they can't return ownership to the same variable if the variable's been invalidated. So let me just go here. Okay, just get rid of this stuff here. Okay, so let's go. Okay, so first thing we do here is we jump into this make string function, and this make string function makes a new variable and then transfers it out, transferring the ownership as well. So ownership of that string memory is transferred to S1, and we can then print it out. And what we can do is, let me just get rid of this. So now for greet, I'm going to return. So let me go. Okay, so we take a string in, we work with it, and then we return it. Where's that complaining? Ah, it doesn't know. Yeah, fair enough. So now we're getting a variable back, but we can't store it back into S2. S2's donezo, it's gone. So now what we can do is put it into S3 and print that out. Okay, so again, we take in a variable, we get ownership of it, we work with it, and then we transfer ownership back to a new variable. We have it. Get ready for this. Hello world. Okay, excellent. So, up to this point, it would seem that ownership is a good idea. It seems to make sense. Also seems a little perverse because, well, how are we going to get around if the only way to work with things is to pass them in and then store them into new variables? There's only so many letters in the alphabet after all. And yeah, totally makes sense. So what we can do is we can work with references. Now, references if we think about ownership, we want to also think about the concept of borrowing. So let's see. Yeah, let's go S2. And then just make a function. Okay, so this is sort of what we want to do. We want to take in a variable, pass it in, get its length, and then still have ownership. So we want S2 to still own the string hello. And the way we do that is we pass in and we say, okay, this is a reference to a string. And we can go, there we go. Put that in, and here S2 is not transferring ownership to this temporary variable. It is letting this temporary variable borrow it. And when line goes out of scope and is destroyed, S2 still has ownership because S2 never gave ownership, it just borrowed. You know, let the other one borrow it. You know what I'm saying. Uh-oh, what's going on here? Oh, no, it works. It's just warning. It's just warning that I'm not using functions. That's fine. Okay, so where are we? So we put out hello and the length, which is 5. And yeah, there we have it. So now let's make another one. I know, I'm being very imaginative with my variables. Okay, so we're going to have a string that we can work with, and yeah, let's use this one. Greet. Actually, yeah, let's do this. Let's go hello, and then greet will make it hello world. Okay, so going down here, we have we're going to have new line, and new line, I want it to be a reference to a string, but I want it to be a reference to a string where I'm treating that string as mutable. So say reference to a mutable string. So what we can do is go with that. I wonder if I can just not return. Because we take memory, we work with the underlying memory. I don't think we even need to return. Let's see how this works. So what we'll do is we'll go, I think I need to also do that. Maybe? Yeah, okay. Cool. So we pass in a reference and we specify that this is going to be a reference to a mutable object. And then we mutate the object by putting on world and then print that out. Yep. Hello world. Awesome. So yeah, it may seem that even though this is a good system, it constrains us, but actually once we get comfortable with using references, it's not too bad. There are just a few caveats to that. And that is that we can only have one mutable reference to an object at any given time. So we can sort of see that in this code. Okay, so I've got a line. I'm going to say, okay. Okay, so we have a reference to a string, and then I'm going to say, okay, let's do that again. That was fun. Let's do that again. And fingers crossed. Oh, seems to work, but it shouldn't work because here's what we're going to do. We're going to So the thing is as well with references, the reference exists from the line in which it's created to the last point in which it's used. So if we sort of print out these references, then it's going to complain because it's saying we can't ignore this any longer, right? We've got a mutable reference, we've got another mutable reference. Hey, buddy, what's going on here? We can't have 2 entry points into modifying a variable because this is a nightmare. This is a recipe for disaster. So what we can do, there's different ways to do things. So let's say what we want to do is we want to go it's bad. So we want to sort of pass that in. What we can do is sort of get rid of that. So I know this is sort of cheating because now we're not working with R1 anymore. So we make a reference, we do our work with it, and then we can proceed from there. And another thing we can do is we can't have, okay, let's go. Okay, so this is bad. We can't have several mutable references. We can have, where are we? We can have several references. But this is a little esoteric here. So what we have is the original line itself is mutable, and so we can't, this still counts as more than one mutable reference because we could modify the original line or we could modify R2. That's 2 different entry points to modifying a variable. That's a bad thing. So what we can do is sort of have as many fixed references, but just one sort of point of mutation, if that makes sense. Anyway, so this has been my little Rust session. I hope this is fun. I hope this is sort of baking in the core concepts of Rust, because I want to focus on sort of the points of difference. And then after that, go back and revisit the fundamental variables, functions, all that sort of stuff. Anyway, hope you had fun, and I'll see you in the next one. Bye.